Hello everybody, this is a lecture on section 5.6 on the ratio test and root test. So we'll start with the ratio test. If the limit as n goes to infinity, absolute value, an plus 1 over an is less than 1, then the series an equals 1 to infinity converges absolutely. If the limit as n goes to infinity, an plus 1 over an is bigger than 1, then the sum n equals 1 to infinity of an diverges. If the limit as n goes to infinity, an plus 1 over an equals 1, then the ratio test is inconclusive. Okay. Notice that in here with the ratio test, in these three possibilities, here the series converges absolutely. Here the series diverges. And here you don't know anything. So none of the outcomes are converges conditionally. Okay, so conditional convergence happens in this area, or it might happen in this area, but the only place it could happen would be here. And here the ratio test just simply tells you nothing, but we've got all these other tests that, that we can use, comparison tests and such, to deal with that situation. Let me give you a basic idea of the proof rather than a formal, the formal complete proof, because, maybe that's just a little bit much right now. But the main idea of the proof is as follows. Right, as n goes to infinity, right, that is when n gets really large, okay, an plus 1 over an, absolute value, is very, very close to L. Very, very close to L. So an plus 1 is very, very close to L times absolute value an. Okay, and then an plus 2 will be very, very close to L times an plus 1. The one right, n plus 2 will be very close to L times an plus 1, which is very close to L times L an. An plus 3, right, will be like L times an plus 2, which will be like L squared an plus 1, which will be like L to the third an, etc., etc., etc. So as the series moves on, when n is really large, an plus 1 plus an plus 2 plus an plus 3 is very close to, well, oh, sorry, absolute value, of all those, an plus 1, an plus 2, an plus 3, plus so on and so forth, all the way out to infinity. The whole sum is very, very close to absolute an times 1 plus L squared plus L to the third, so on and so forth. And what's that right there? This is a geometric series. Right, and the geometric series converges when L is less than 1, diverges for L is bigger than 1. Right, which converges for L less than 1 and diverges for L bigger than 1. When L is equal to 1, other considerations come into play. Okay, this isn't really, a formal proof, but it's the general idea. Essentially, with the ratio test, the series is like a geometric series after a while. After a long time, it's basically a geometric series. When n is really big, and we know when those converge and when those diverge. Okay, so let's take some examples. So the sum n equals 1 to infinity, 3 to the n over n factorial. Okay? Let's make it alternating. Why not? Minus 1 to the n times 3 to the n over n factorial. So here, converge absolutely. Diverge. Okay, well, here an is equal to minus 1 to the n, 3 to the n over n factorial. But we're dealing with absolute value here, right? So that minus 1 to the n essentially goes away, because it's either, plus 1 or minus 1, so you're just left with this. So now, the limit as n goes to infinity, an plus 1 over an in absolute values is equal to 3 to the n plus 1 over over n plus 1 factorial over 3 to the n over n factorial. Oh, I forgot my limit. So this is the limit as n goes to infinity. And what we're left with is n factorial over n plus 1 factorial times 3 to the n plus 1 over 3 to the n. Now, with factorials, right, n plus 1 factorial is equal to, let me do it over here, is equal to, well, it starts at n plus 1, then it goes down to n minus 1, n minus 2, all the way down to 2 times 1. Right, but this bit of it right here is just n factorial. So n plus 1 factorial is n plus 1, the number, times n factorial. Right, and we can use that here to do some cancellations. So this is equal to the limit as n goes to infinity, n factorial over n plus 1 times n factorial. And then this is 3 times 3 to the n over 3 to the n. Cancel, 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 cancel. So this is the limit as n goes to infinity, 3 over n plus 1, which is 0, which is less than 1. So this guy converges absolutely. Okay. Similar example. So sum n equals 1 to infinity minus 1 to the n, 3 to the n over n squared. Okay, so here, so converge absolutely, or diverge. Okay, well, the limit as n goes to infinity, absolute value of an plus 1 over an is equal to the limit as n goes to infinity. So we're talking absolute values, so this minus 1 bit goes away. So we have 3 to the n plus 1 over n plus 1 squared over 3 to the n over n squared. So this is the limit as n goes to infinity, and we're left with n squared over n plus 1 squared times 3 to the n plus 1 over 3 to the n. So this is the limit as n goes to infinity, n squared over n squared plus 2n plus 1, and then this is just 3. This limit, because it's a square polynomial over a squared polynomial, well, not squared polynomial, it's a degree 2 polynomial over degree 2 is 1, and this limit here is 3. So this is 3, which is bigger than 1. So sum n equals 1 to infinity minus 1 to the n, 3 to the n over n squared diverges. Okay? So there's the ratio test. And we will make use of the ratio test in the next section as well, section 6.1. But there's just a couple of examples to get us started. The next test, the root test, is very similar to this. Okay, if the limit as n goes to infinity of the absolute value of an to the power 1 over n, in other words, the nth root of that, is less than 1, then the sum of the an's converges absolutely. And then if that limit is bigger than 1, then the series diverges. And if it's equal to 1, then it's inconclusive, the root test. So if this is bigger than 1, and this diverges, and if this is equal to 1, then the root test is inconclusive. Okay, so for example, let us consider number 335 in the section. The sum n equals 1 to infinity 1 over e plus 1 over n to the nth power. Now, converge absolutely or diverge. Alright, well, the limit as n goes to infinity, this is already positive, so we don't have to worry about absolute values. So this is an, and that whole thing in the root test is to the 1 over n power. Right, but n times 1 over n, because you multiply the exponents, is 1. So it just becomes that. Which is equal to, well, this is 0, and that's 1 over e, which is less than 1. So the sum, n equals 1 to infinity, 1 over e plus 1 over n to the n, converges absolutely. Okay. Similar to this, let's look at this one. So let's put, instead of 1 over e, let's put e. Well, here the limit as n goes to infinity of e plus 1 over n to the n, that whole thing raised to the 1 over n power, the nth root, is equal to the limit as n goes to infinity, just e plus 1 over n. These are multiply and go to 1. So that's equal to e plus 0, right, which is bigger than 1. So this guy diverges. Okay. Let's put a question mark there. All right, so a couple simple examples using the root test, and we'll go over more of those in class, and that is the lecture for this section.